Our next speaker is a research scientist at the NIH Center for Translational Therapeutics. He handles all of their small molecule and RNAi informatics. Please welcome Rajarshi Guha.
Thank you for the invitation to speak here today. Today I'm going to be talking about fragmenting molecules, or smashing molecules as we like to call it, and some of the uses of fragments that we or some of the applications of fragments that we use at the NCTT as part of our high throughput screening efforts. I would like to point out, usually I don't look like that. It only happens when I'm stuck on a slow computer or a slow network. This is joint work with my colleague Trung Nguyen, who has implemented a lot of the stuff I'll be talking about in user-facing applications. The outline of my talk starts off with my view of fragments as the building blocks of chemistry and representing sort of a background for subsequent analyses of bioactivity and lots of structures. I'm going to touch a little bit upon fragments and SAR, and then focus mainly on the topic of fragments and what we call activity profiles. Stepping back from our usual day-to-day work of trying to correlate bioactivity with small molecule structures, I've had some interest in big data. It seems to be a rather hot topic these days with a lot of companies and a lot of areas talking about it. And there was an interesting paper sometime back by Halevi et al. Who discussed the effectiveness of very large data sets. And their application focused on machine translation using statistical approaches. And they pointed out that the larger the corpus you had, a good example is a Google Ngram corpus, the better that the machine translation ended up working. And they suggested that the effectiveness of these large data sets is because, at least for the Google Ngram corpus, is that they encompass all the commonly used phrases. Now, it would be probably not really scientific to extend that to every large data set that comes up, and certainly they focus just on machine translation. But what would be the equivalent of an Ngram corpus in chemistry? And one way to look at that is to consider fragments. And we can actually make a much more direct analogy with Ngrams if we consider lingos, which are simply smiles chopped up. Now, it's possible to generate arbitrarily large virtual libraries and from them arbitrarily large fragment collections. But then, by analogy with the Halevi paper, would such a collection span all of commonly used chemistry? And depending on the initial compound set and what you're looking at, one could say yes. But in many cases, especially in the work we do at the NCTT, where we're doing probe development, we're interested in going beyond such a commonly used set of, or commonly used chemistry space. Just to point out a little bit on how many fragments do we get from, say, commonly used collections in high-throughput screening and what is their diversity. If you consider a set of bioactives such as the low-pack collection, which is used for validation screens, it contains 1,280 compounds. And using an exhaustive fragmentation scheme, that gives us just under 2,500 fragments. If we go up to the whole molecular libraries screening deck, that's right now about 372,000 compounds, that gives us about 640,000 or 164,000 fragments. And the graph on the right-hand side shows the distribution of the fragment frequency or frequency of fragments in the or the frequency of molecules containing those fragments. When we look at, say, one measure of diversity of the fragments, we get something that looks like this, which is a representation of the molecular libraries fragments in a B-cut space. It's an interesting pattern. It seems to hold up on smaller subsets if you don't go through the whole library. And I just bring this up to highlight the fact that for the molecular libraries collection, as an example, we get this type of distribution in one chemical space. There are certainly many others that you could look at. That's not the main focus of my talk today. The thing that we want to ask ourselves is, given a large screening collection or any library that you're working with and generating fragments from that, what can you do with them? Is it actually useful to go through this process? So There are a number of uses. One obvious use is to learn from fragments, build QSAR models, make predictions. An interesting paper recently described generative models based on fragments. Another way is to avoid standard clustering approaches on very large libraries and use fragments as filters and grouping mechanisms. Obviously, exploring series and chemotypes and their associated activity, looking at scaffold level promiscuity, and so on. So from the point of view of my day job, which is analyzing high-throughput screening data, I'm interested in, say, doing cherry picks and using fragments to let me select a good initial subset of active compounds that hopefully will confirm in the secondary screens. So one of the things we want to do is to identify interesting scaffolds, or useful scaffolds, and observe or explore the activity in the molecules that contain those scaffolds. So one example of a tool that we've released, or rather my colleague released, is a network-oriented view of scaffold collections. I'm using scaffold and fragment interchangeably. I will address this issue in a few slides. And this is actually similar in idea to the Scaffold Hunter tool that was published some time back. It's not a purely hierarchical representation, but I'll say at this point that it's interesting. You can load in arbitrary data associated with structures and then color them by, based on data ranges and other properties. And in our experience or experiments with this, it seems to give us a way to quickly assess the utility of a scaffold. The link down there lets you try it online. It's an application, a JNLP application, so it should start without any problems. Okay, so we can fragment our library. We associate bioactivity with those scaffolds, but we still have to ask the question, what is a good scaffold? Just purely looking at, say, the maximum activity associated with the molecules containing that scaffold is just one measure. There are many others. How big is the scaffold or the fragment? How complex is it? And I think more fundamentally, do the members containing that scaffold represent an SAR or not? And one thing that I have learned in my experience is that intuition and experience play a big role. There are many cases when I'll be talking with a chemist and bring up a scaffold that has interesting numerical properties. They will look at it and say, no, this is not a scaffold. We need to do something else. So there is medicinal chemistry intuition that is playing a big role in the scaffold selection process. And in the past, I've been doing some work. We're looking at structure activity landscapes. And one of the ideas I've been exploring a little bit is, can we take scaffolds and their associated bioactivity data and ask, what do the landscapes associated with these scaffolds look like? Ideally, we'd like a landscape that is relatively smooth, but with a few peaks representing interesting SAR, as opposed to a flat landscape where there's no SAR, or a extremely pretty much random landscape where if you change anything, you lose all your interesting properties. So one of the things we've been looking at quantifying is something that we're calling Scaffold QSAR. Essentially, can we numerically quantify whether a scaffold and its associated members contain or represent any SAR at all? And the idea is relatively simple. Given a scaffold and its various members, we identify or we evaluate the set of descriptors, topological or physicochemical descriptors for the individual R groups, and then throw that into a modeling routine, usually PLS or ridge regression model, because usually these are very small, few observations, and then try and predict the activity and compare it to the observed activity. The key thing to note here is that we're not really interested in whether we accurately predict the observed activities. What we're really interested in is a statistically significant model, not necessarily the most accurate model. And given the fact that many of these scaffolds won't have a fully populated R group table, means that we're probably not going to get accurate predictions anyway. But the presence of a statistically significant model could suggest that there is an SAR being encoded by the molecules that contain this scaffold. And we've run a few experiments, and we seem to be pulling out interesting structures or interesting scaffolds that seem to hold an SAR. But as you would expect, there's a number of obvious drawbacks here. Most scaffolds are going to have very few members in them, so building any type of model on 5 to 10 observations is probably unreliable. In addition, and a side effect of this is that most of these models are going to have more features than observations, which makes actually modeling them a little tricky. It does work better for combinatorial libraries where sort of by definition you don't have such a sparse descriptor matrix. And obviously, I mean, a linear fit, which is what we've been playing around with up till now, may not really be the best approach to this, but a priori it's difficult to choose a more sophisticated model. So that's one way to look at fragments and try and answer the question of which fragment should we follow up. The other thing that we've been focusing on now more as an exploratory approach is what we're calling fragment activity profiles. So when we're looking at scaffolds in the HTS triage process, we usually end up asking one of two questions, or maybe both of them. What is known about this chemical series with respect to the intended target, and what compound classes are known to modulate the target that I'm looking at, and how similar are they to the series that I've got out, say, from my primary screen? So really what we're looking for is exploring activity data in bulk grouped by scaffolds and targets. Our approach to answering this question is based on the ChEMBL database. All the slides I'm showing you are based on version 8 of the ChEMBL database, but as I'll show, it's very easy to update this to the latest version. And the idea underlying this is that ChEMBL contains a lot of bioactivity across multiple targets. And we essentially pre-process the database by generating scaffolds using an exhaustive enumeration of combinations of SSRs. But this is just our particular approach. You could use any fragmentation scheme you wanted. And then we normalize data across assays, or normalize data in each assay using by converting the activity values to z-scores that allows us to compare the activities across assays. I'll just point out here that everything that I'm describing for this procedure is available for download. The pre-processing steps are encoded in a servlet, so you can download the zip file, throw it into a Tomcat container, and assuming you have ChEMBL installed in an Oracle instance, just visit a link and it does all the pre-processing steps. So it'll fragment all the structures in the instance of ChEMBL that you have and evaluate a number of useful properties. It'll aggregate the assay data. For our experiments, we only consider assays with IC50, so we ignore Ki, Kd, and those things. The reported unit is nanomolar, and there should be no uncensored data. And we also restrict ourselves to assays with more than 5 observations. And finally, we end up with a set of robust, that is, instead of using the mean and SD, we use the median and MAD z-scored activities. So what do we get out of this? We can pull out some statistics. So on the left-hand side here, we see a distribution of the number of molecules and how many assays or how many assays contain what number of molecules. This is a log scale here. So the bulk of ChEMBL assays contain between 10 and 100 observations. There are relatively fewer assays with many thousands of observations. What is the distribution of z-scores across all the assays out here? In this case, I've artificially cut off very high and very low z-scores. So I'm using a range of -40 to 15. But you can see that more than 50% of the z-scores lie around 0, so just at the mean of the mean activity within any given assay. It turns out that there are just under 13,000 molecules that lie outside this range, and the bulk of these have z-scores that are far, far smaller than -40. One might think that these are really active molecules, but the fact is you can't really differentiate between really active molecules and experimental outliers just by looking at the numbers here. You'd have to go back to the original publications. So once we have this in place in our Oracle database, we can start pulling out individual fragments and looking at the molecules that contain those fragments and start generating profiles. So we identified, for the purposes of this talk, fragments containing 8 to 20 atoms and occurring in 100 to 900 molecules. And this gives us a set of just under 1,800 fragments. And here's the distribution of the number of molecules and the percentage of fragments that occur in them. And you can see that there's a bunch of fragments that occur in a relatively small number. molecules, and then we have a few fragments that are occurring in a large number of molecules. What we're interested in fundamentally is what is the activity distribution associated with a fragment. And we can query the tables directly and then generate summaries using Java. I did these in R and so on. So we can go through individual fragments and plot the histograms of the activity distributions. Here, n corresponds to the number of molecules containing that fragment. And you can see some differences in the distribution here. And in this case, we're using the full range of z-scores, so I'm not censoring any data. But this is certainly handy for me to do because I live in R. But when we're talking with chemists and really want to avoid writing code, it's useful to encode this procedure in a more user-friendly application. So my colleague Trong put together our fragment activity profiler application, which essentially provides us an interactive interface to all the data that we generate here. So on the left-hand side view here, we have individual fragments that we've generated from the ChEMBL dataset. And when you select a fragment, the activity histograms will show up in this panel here. The first column considers or doesn't consider any assay grouping. So it's the distribution of z-scores across all the assays that a molecule is tested in and has the fragment that was selected. But then we also make use of the ChEMBL target hierarchy that allows us to then break down this distribution into a target-wise distribution. When you select, say, a given target-wise distribution, we then list the molecules, highlighting the occurrence of the fragment in them, and then list the actual activity values that were reported for that molecule against that target from the ChEMBL database. And this way, it's we can then start browsing the fragments in a more intuitive manner rather than having to write R code or Java code to query databases. It's useful to look at fragments that we generated from ChEMBL, but probably more of interest to someone trying to use the ChEMBL fragment collection as a sort of background or provide context to their own structures is to draw your own structure in there and fragment on the fly and then look at the activity distributions of those fragments in ChEMBL. And that's exactly one of the things that we support here. We bring up the sketcher, draw in our molecule, and on the fly generate fragments and then pull those fragments and the activity distributions for them out of the database. As I said, we employ the ChEMBL target hierarchy. By default, if I recall correctly, we use the L3 level, which is a rather high level. So one of the groupings would be kinases rather than individual kinase targets. But it is possible for the user to either go up the hierarchy to a more broader classification, or go further down and start looking at histograms against individual targets. So that's one way to browse specific fragments, bring up your own fragments and look at the activity distributions for them. But we can start asking some interesting questions. One of the common sort of principles of drug discovery is that similar structures have similar properties. Can we extend that and ask, do similar fragments have similar activity profiles? So as an example, we considered 658 fragments that contain more than 10 atoms and occurred in 500 to 1200 molecules. And we evaluated the Tanimoto similarity between each of these between each pair taken from these 658. And overall, the fragments tend to be rather dissimilar. The 95th percentile is just 0.50, and this histogram shows the distribution of Tanimoto similarities. But from this subset that we looked at, it turns out that 1800 pairs do exhibit a Tanimoto similarity greater than 0.8. So the question is, do these supposedly similar fragment pairs show correspondingly similar activity profiles? And it turns out that that's not the case, really, which in hindsight is obviously not too surprising. So what we do here is for each pair of fragments, we pull out the activity distribution and we compare them using the Kolmogorov-Smirnov statistic. And this plot summarizes the analysis for all pairs from that 658 fragment subset, where the x-axis is the Tanimoto similarity of the fragments or the fragment pair. And the y-axis is the Ks statistics, or the D value in the usual definitions. And a higher D value corresponds to a bigger difference in the activity distribution profile. The color coding is the p-value, which is for the test itself. And bluish here corresponds to very poor p-values. Closer to 0 means the test was statistically significant. And you can see that there are a bunch of pairs which have a Ks statistic close to 0, which is, at least on the face of it, very similar distributions. But their p-value is close to 1, which means it's not statistically significant. But the bulk of it has a Ks statistic that's non-zero, and these are statistically significant, indicating that most of these activity distributions are different, even though the Tanimoto similarity might be high. And one of the key things to realize is that this is not necessarily a fully rigorous analysis, because many of these fragments will only have a few members in them, so the distribution itself is very crude. So again, that analysis was done in R. It's very easy to script that, querying our database. But again, for a non-cheminformatics person who doesn't do this all day long, we'd like a application that allows us to look at pairs and compare distributions in a much easier manner. So again, the fragment activity profiler allows us to select fragments and then look at them in a pairwise manner, where on the diagonal we get the activity distribution of that fragment only. But then on the off-diagonal entries, we can then compare the activity distributions for the given pair of fragments that lets us quickly browse through them. So another question that is of interest is, are fragments selective? This leads to the idea of, comes from the idea of promiscuous scaffolds or promiscuous fragments. And again, this is something that you could do by browsing through the application interface, but obviously it becomes a little tedious if you're trying to go through the whole of ChEMBL. So this is one type of analysis that we haven't coded up in the application yet. This is something that we do outside of the application. And what we'd like to do is identify fragment pairs with very different activity distributions, or fragments that have a preference for a certain target or a target class. I'll just show two quick summary visualizations that we have, where we take a fragment and evaluate the mean activity of the parent molecules, or the molecules containing that target, containing that fragment, grouped by target classes. And we also count the number of parent molecules tested against that target. So we get a plot that looks like this, where the y-axis is the mean activity of the molecules containing that fragment, and the color coding corresponds to the number of molecules tested against a specific target. So this is one example that we were able to pull out that matched, or we had some evidence for in the literature. The 1-phenyl imidazole structure has been noted in the literature as having a preference for the CYP450 target, and that is what turns out from the ChEMBL data. Another example is the benzyl pyridine fragment. In this case, the literature reports it as being selected for dopamine agonists. In this case, however, the ChEMBL data doesn't correspond to that. So this is not a foolproof way, and again, it's really dependent on what ChEMBL has curated there. So it's not a foolproof way to say that based on these distributions that a given fragment has this specific preference, but it is an interesting way to explore and an interesting way to generate ideas. The last thing that I wanted to touch upon is the fact that I've been using fragment and scaffold interchangeably, and this is not always true. And as I mentioned before, chemists have an intuitive idea of what a scaffold is, which doesn't always match up what the numeric data tells us. So one thing we'd like to do, or try to do, is somehow encode the idea of scaffold-like or fragment-like. And one thing that we've come up with is based on the concept of signal-to-noise ratio, which in its traditional definition is the mean of the signal divided by the standard deviation. And we've repurposed it so that the mean is replaced by the size of the fragment, and the standard deviation is the standard deviation of the number of atoms in the parent molecule that are not in the fragment. and this is considered over all the parent molecules containing that fragment. So essentially, it gives us a measure of the variation of the molecule that is not part of the fragment that we're looking at. It's not a perfect definition, as you would expect for smaller fragments which are which occur in lots of molecules. The SNR value gets skewed towards smaller values, this matches up when we look at a plot of the fragment size versus the SNR value. Smaller fragments tend to have smaller SNR values. Also, given the ChEMBL database, this is the distribution of the SNR value, and you can see that the bulk of the fragments have very low or very small SNR values. Again, this is a very open question. It's just one measure that we've come up to try and address the issue of what is a good scaffold versus a fragment. And it seems that from our, at least eyeballing the data, that higher SNR values tend to be more extended Merkle-like fragments. But again, it's easy to find exceptions where high SNR values aren't necessarily very extended. Correspondingly, smaller SNR values, we think, which is a little arbitrary, values less than 2 correspond to more fragment-like versus scaffold-like. And these are some examples of fragments with small SNR values. But again, it is not difficult to find counterexamples where you have a extended fragment that has a low SNR value. So the last thing to that we looked at up to this point is, okay, so if the SNR is designed to try and identify fragment-like versus scaffold-like, does that affect the activity distribution if we consider molecules as containing, as being, or molecules divided or grouped into whether they show more variation versus less variation in the portion that is not part of the fragment? So to look at this, given a fragment, we evaluate the standard deviation of the number of atoms in the parent molecule that are not part of the fragment, and then we label each of the molecules as being core-like, non-core-like, if the number of atoms is not in the fragment is greater than that standard deviation. Otherwise, it gets called core-like. And then we look at the activity distributions of the parent molecules. Unfortunately, this hasn't proved to be very successful. Here are 2 fragments with high SNR. And if we look at the distribution of the core-like group versus the non-core-like group, there isn't a whole lot of difference in these distributions. And this holds for different fragments, for high SNR or even low SNR. In this case here, we do have a few outliers, and we do find a few cases where there are fragments where the bulk of the distribution looks very similar. The differences occur in some of the outliers. And we're still not sure exactly what that means, and it's something that we're looking at. I'll end here by just summarizing that we have all of this can be replicated. Scaffold Activity Networks, this link will start the application. For the Fragment Activity Profiler, as I mentioned before, all the SQL needed to generate these extra tables for the ChEMBL database, as well as do the fragmentation and property computation, are available here. If you want the client sources, they're available here, and you can simply run the online version, which will let you draw in your own fragments and look at your own data from the last link. And thank you for your attention.